Hello everyone, this is Martin from Kyoto University. Today I would like to present our solution to creating new bilingual dictionaries from existing dictionary resources. What is bilingual dictionary? It is machine-readable language resource used to translate one language lexicon to another. It is also a very valuable resource for many tasks in natural language processing and useful for end users. Unfortunately, high-quality dictionaries are only available for popular languages, but they remain sparse, dated, or simply unavailable for less resourced language, such as many Turkic languages. For example, there are at least 35 Turkic languages in use mainly in Central Asia, which have about 170 million speakers. But there are a few dictionaries available for those languages in between, and they are in very small scale. And also, the recent studies claim that dictionaries of related languages are very useful for making machine translation systems. Most of the resource-poor languages or less resourced languages have bilingual dictionary to or from a major language. For example, we have a dictionary between Uyghur Chinese, Kazakh Chinese, Kyrgyz Chinese, and as well as English, Russians, but we don't have a dictionary between the less resourced languages. And also, large number of bilingual dictionary resources are being accumulated and exposed as web services, such as in Language Grid project. So the question here is, how can we create new dictionaries using these existing dictionaries? And its simple answer is pivot-based dictionary induction, where if we have a two dictionary from A language to B language and the B language to C language, then we simply connect these two dictionaries through B language to create a new dictionary between A and C. Let me explain this idea by an example. Assume that we have a dictionary from Uyghur to English, from which we take a Uyghur word and its English translations. And we have another dictionary from English to Kazakh, from which we can take Kazakh translation of the English word. And by this whole connection, or let me call this as a pivot graph, we can get Kazakh translation of the Uyghur word. In other words, now we can create a new dictionary between Uyghur and the Kazakh. Unfortunately, the second pair is not correct, and this is a word sense ambiguity problem. The reason for this happening is that the lexicons are generally intransitive, and this intransitivity stems from polysemy and the ambiguous words. Without properly solving this ambiguity problem, the pivot-based process may produce a very noisy and low-quality dictionary, and identifying correct or incorrect translation pairs during the process is very challenging without knowing the knowledge of sense data. Let's have another example. This is a real pivot graph for the real dictionaries, in which there are 2 Uyghur, 3 English, and 3 Kazakh words, and which produce a new dictionary contains 6 pairs. And let's observe the sense. When we observe the senses, either U1 and U2 should not be paired with K2 because they have totally different sense. But this happened, they are paired because the E2 is a polysemy word which has 3 meanings from S1 to S3. So when we consider the sense information, the correct output dictionary should only contain 3 pairs. So how to identify this kind of correct or incorrect pairs? Most of the existing studies propose to use extra resources to solve such a problem. For example, using post-stagger to match the part of speech, and using parallel corpora to count the co-occurrence of the word pairs, and recently people use comparable corpora as well. And these kind of approaches are well accepted. They are good in performance, but they are still high resource demanding, so we need some external resources to implement this approach. And there is another approach which only use the inherent structure of the original dictionaries. So the idea in this approach is that the more meanings a word pair share, the higher likely they are a correct pair. For example, if U1 and the K1 share two meaning, while U1 and the K2 share only one meaning, and we can assume that U1 and the K1 is more likely to be correct. And if there is even more meaning, and we even can put a higher score to their correctness or the reliability. So this kind of approach are usually low resource demanding, so there is no need for extra resources, but generally low in precision. We in our paper proposed a constant optimization approach to pivot-based dictionary induction to promote the overall quality in case of closely related languages. Now, our approach does not require external resources, but in order to take into account the word senses, we use an approach based on semantic distance, in which possible missing meanings are considered because existing dictionaries are often incomplete. And the lexicon similarity of intra-family language or closely related language are generalized as a constraint, based on which the pivot-based induction is modeled as an instance of optimization problem to generate a new dictionary. And also we further extend this optimization approach by utilizing more dictionary resources. For example, if there are more than two closely related languages have bilingual dictionary between a pivot language, like Uyghur English, Kyrgyz English, and Kazakh English, we try to combine all these dictionaries into one big graph to create a new dictionary. And our assumption is that incompleteness of existing dictionaries are different, and we try to take advantage of more complete part of each dictionary on measuring the semantic distance. And we also expect higher accuracy and scalability when there is a new dictionary involved in this induction process. Let me show you a graph. This is a lexistatistical matrix of Turkic language, which shows the percentage of cognate pairs shared among the major Turkic languages. And in this case, a cognate pair is a pair of words coming naturally from the same root with possible spelling difference due to subsequent separate phonetic development. In translations, in most cases, cognate pairs are considered as direct translation or just one-to-one mapping. For example, in Uyghur and the Kazakh, they share their lexicons up to 82%. We have seen in the previous slide that intra-family languages share large parts of their lexicons. For example, in case of Turkic language, it is from 44% to 94%. So considering this fact, we started our solution by assuming that lexicons of intra-family language are one-to-one mapping or word-to-word mapping. And this assumption states that given a two intra-family language, any word in one language has its unique equivalent in another, where they share exactly same meanings. So when we try to interpret this statement in terms of a pivot graph, it can be a one-to-one pair has symmetric connection via pivot words. For example, in this pivot graph, if U1 and the K1 and U1 and the K1 is a one-to-one pair, then we can say that there is an edge between K1 and the E3 is possibly missing, because there should be a symmetric connection between U1 and the K1, but actually there is one edge is possibly missing. In the same way, if U2 and the K3 is a one-to-one pair, we can say that there is another edge between K3 and the E2 is possibly missing. So if we assume that the original pivot graph is complete, it should be like this. And overall, we regard this one-to-one mapping assumption as a constant. And a pair of words must satisfy this constraint if it's a one-to-one pair. And also, by adding the missing meanings or missing edges into the pivot graph, and we can find more and more one-to-one pairs. We define a weight for a possibly missing edge as a chance or likelihood that the edge is really missing from the original dictionary. And the value of the weight ranges from 0 to 1. The higher weight means the edge is more likely missing. So in order to obtain these weights for all the possible missing edges, we first list all the possible one-to-one pairs from the original pivot graph. Then we use a statistical calculation to approximate probability that each one-to-one pair candidate to be a correct one-to-one pair. So for example, in this pivot graph we got 6 one-to-one pair candidates, and then we try to distribute all these values to the relevant edges to get a list of possible missing edges and their weights. When there are more dictionaries are involved in the induction process, or for example we have 3 input dictionaries, the weight of the possible missing edge is independently calculated in each 2 combination of the dictionaries, and a maximum is shared. For example, from the Uyghur English and the English Kazakh dictionary, we can get a particular weight for a particular missing edge. And in the same way, from the Kyrgyz English and the English Kazakh dictionary, we can calculate the weight for exactly same edge. So then we get the maximum of these 2 weight as the final weight of a given missing edge. Once we have the list of one-to-one pair candidates and the possible missing edges with their corresponding weights, we try to model the process of selecting the correct one-to-one pairs as an optimization problem. Therefore, we define some variables, like x is a variable indicating whether a word pair is a one-to-one pair, and y is indicating whether a edge is missing. And as for the objective functions, we define 2 objectives. One is we have to find as many as one-to-one pairs, or we have to maximize the coverage of output dictionary. Meanwhile, we have to minimize the number of adding incorrect meanings, or we cannot add many edges into the pivot graph because the original dictionary is created by humans, so we have to believe its structure is correct. And these objectives should subjective to some constants derived from our one-to-one assumption. For example, a one-to-one pair must have same meanings, a one-to-one pair must be unique, and a one-to-one pair should be consistent across the intra-family language. In order to formulate and to solve our problem, we need an optimization framework. Obviously, our problem can be seen as Boolean-based optimization, because facts like whether a pair is one-to-one pair, whether an edge is missing are all binary states. And there are some good candidates like maximum satisfiability or maxsat or pseudo-Boolean optimization, because maxsat and the PBO have very good algorithms developed recently, and also they can often be translated each other. So in our particular case, we choose PBO due to easier formalization of cardinality constants. It is also known as a 0-1 linear programming in the ILP community. PBO often has an objective function, which is a linear term that should be minimized or maximized. And this is its general form, and we try to formalize our problem based on this general form and to solve using a solver. Here is a linear expression of our overall objective function, which consists of two parts. And first part represents our objective to maximize the number of one-to-one pairs. So it is the summation of all the x variables which represent the one-to-one pair candidates. And the second objective represents our objective to minimize the number of adding incorrect meanings. We also put two parameters, varph1 and varph2, and during the experiment we observed that by adjusting value of this parameter, we can somehow balance the precision and the recall of the output dictionary. And we also formalized the constraints. The first constraint is any one-to-one pair must have same meanings, and this is the linear expression. For example, in this pivot graph, if U1 and the K1 is one-to-one pair, then 6 edge, all these 6 edge should exist. Or in this expression, if x, the value of x variable is 1, then in order to satisfy this inequality, the value of all these y variables should also be 1. The second constraint is any one-to-one pair must be unique. It is obviously a at-most constraint or cardinality constraint, which say that for any set of n one-to-one pair candidates which share a common word, then at most one of them can be one-to-one pair. For example, in this case, U1 has a two candidate, K1 and the K2, but we don't allow both of them to be one-to-one pair at the same time. So in order to do that, we just write in a simple linear expression like xu1 k1 plus xu1 k2 should be equal or less than 1. The third constant is one-to-one pair should be consistent across the intra-family language. And of course, this is the case of we have more than two input dictionaries. In order to express this constant, we can simply write this kind of expression. But unfortunately, the ILP does not allow the unequal operation, so we have to convert this expression into corresponding and valid linear expression. We designed a tool to implement our solution, which uses IBM CPLX optimization library as its default solver engine. By using this tool, we conducted an experiment for an evaluation purpose. Here is the experiment settings. We got 3 dictionaries from Chinese to Uyghur, Chinese to Kazakh, and Chinese to Kyrgyz, where Uyghur, Kazakh, Kyrgyz are related languages while Chinese is distant. We separated experiment into 2 parts. In the first part, we only use 2 dictionaries to create new one. For example, we use Chinese Kyrgyz and the Chinese Uyghur dictionary to create a dictionary between Uyghur and the Kyrgyz. And we also use Chinese Kyrgyz, Chinese Kazakh dictionary to create dictionary between Kazakh and the Kyrgyz, and for also Uyghur and the Kazakh. So in this experiment we can get 3 output dictionary, which we call this set as a D. In the second part, we try to combine all these 3 dictionaries into one big pivot graph to create a new set of dictionary. We also can get 3 dictionaries, and we call this set as a D-prom. And we compare the quality of dictionaries in the D and the D-prom. We use human expert to evaluate all these results, and we compare precision, recall, and the F1 measures of each dictionary in the D and the D-prom sets. Here are the structural information of input dictionaries. When we try to combine all these 3 dictionaries into one big graph, it consists of 664 subgraphs or connected components. For the experiment purpose, we only selected smaller subgraphs as a sample, which total include about 2,000 Uyghur, 3,000 Kazakh, and the more than 1,000 Kyrgyz words. And here are the evaluation result, from which we can see that for the case of Uyghur Kazakh dictionary, and we got 80% precision in case of 2 input dictionary are used, and 86% precision in case of 3 input dictionaries are used. And same case for Uyghur Kyrgyz and the Kazakh Kyrgyz dictionaries, although their precision are somehow different from the Uyghur Kazakh dictionary. And for the recall, and we got up to 70% in case of 2 dictionary are used for the Uyghur Kazakh dictionary, and 73%, which is slightly bigger, for the case of 3 input dictionaries are used. And this is also similar for Uyghur Kyrgyz and the Kazakh Kyrgyz dictionaries. In average, we got 4% precision, 2.6% recall, and 4% F1 measure gain when we use 3 input dictionaries. I would like to conclude today's presentation. Pivot-based dictionary creation is promising for inadequately resourced languages. In this work, we proposed an approach to pivot-based process where lexicon similarity in related languages are generalized as constraints. And by taking into account the data incompleteness, the induction is modeled as an instance of optimization problem to generate a new dictionary. Furthermore, we extended the method where more existing dictionaries can be utilized for better output performance. And we showed that utilizing more existing dictionaries yielded slightly improvement either in precision and recall. And we also did another experiment to compare our method to an existing method. And as a result, we got 10% more precision with similar recall. And here is the reference of this work. Thank you very much for your attention.